All right. Welcome back. Before starting, any questions from last class where we review make, and from previous classes where we review modularity? No? Right. So what we're going to be talking today is about arrays and other data structures that you may found useful to know when using C++. So this is the plan for today. So we're going to review arrays, their general use, how you can see them actually as being pointers. We're going to see something about multidimensional arrays, because most likely one-dimensional arrays will not be enough for the kind of work that you probably are doing. We're going to try to understand how these arrays are allocated in memory. This is important to see in the future when we start to deal with libraries, how you can take the best performance of them by understanding how the arrays are actually saved in memory. And we are going to review very quickly some existing libraries and functionalities. Then we're going to switch a bit gears, and we're going to discuss further data structures, more complex and abstract data structures. We are going to talk about lists, trees, the C++ standard template library that brings already some containers for this kind of data structures, and see some examples about it. So let's start by probably motivating why you want to use arrays. Well, if you had to deal with fields, if you had to discretize equations and deal with grids, or doing linear algebra in any kind of flavor, you probably will have to deal with arrays. So it's something that is the bread and butter of any kind of computations, in particular in physics, right? So probably the motivation is not too much necessary, but it's already there for all of us. So let's take a look at how we can initialize, or different ways that we can initialize arrays. So I think Rancis already mentioned a bit about arrays in this in the first lectures where we review a bit about C++. So I have different ways here where I can initialize arrays. These are what are called static arrays, in the sense that you can define the array on the fly in the language. Like, for instance, I have in the first 3 lines, or in the first 2 lines, the array cars with 4 elements, and it's defined, or is initialized with these 4 values, the 6, 8, 10, either by saying the type of the array, the name of the array, the size of the array, equal, and between braces the values, or just writing the braces without the equal. Alternatively, you can say the type of the array, the size of the array, and then immediately define the array. Okay. In this case, this is not allowed. You have to do element by element. Okay. So the second line is not allowed. You have to do it element by element, either in a for loop or setting each of the individual values, like hand of 1 equals 3, hand of 2 equals 6, hand of 3 equals 8, and hand of 4 equals 10. Another thing that is not allowed is to copy arrays in this way. So you cannot identify arrays just by saying this array is equal to another array. There is another way to do that. We are going to see how to do it. This is another option for initializing arrays. So if you want to initialize all the elements in an array equal to a given value, you just define the type of the array, the name of the array, the size, and equal to the value. So it's a specific case or a particular example of the previous ones. Alternatively, and probably the one that we suggest you to use, is to define the type of the array, the name of the array. Don't specify the size, and the size will be given by the number of elements that you have in your definition. Okay? Why is that? Because then you have one less parameter to remember when you're defining your array. Okay, any questions about this? Yep. Depending on the method, so we are going to see, for instance, one library that has its own method for initializing to 0. On the top of my head, I don't think so. The only thing I will suggest you is don't leave it without defining, because you don't know what garbage is in the memory before. So whatever you decide to do, just define it. Who has used Python or R before? Okay. So you know that in those kind of languages, when you hit the end of the array, you probably get an error, right? In the compiler languages, either C or Fortran, that doesn't happen, unless that you put some compilation flag. And this is an example where you will see that we are hitting the end of the array, and the compiler won't say anything. The program will return your value, but that value may be meaningless. Okay, so let's take a quick look at this example. So this is a main function. It has an array A, which is defined as 0, 1, 2, 3, 4. Then it has another way to define an array, which is pointer B, which is an integer of 5. So it's an array of 5 if you wish. And then basically what we are doing is we are initializing the array B with a for loop. And then we are outputting, so the array is initialized in its definition. The array B is initialized with the for loop. There are two different ways of initializing. Then we are outputting the array A, and we are outputting the array B. Okay. Finally, because the array B is allocated dynamically, we had to delete it. Okay, we covered that, I think, right? Finally, we return 0. This is good practice because nothing bad happened in the code, and that's it. Any questions about this? Yep.
Sorry, in that for loop, A goes to 7?
Good catch. Yes. That's exactly the point. Yes. So that for loop involves, when we are outputting, is going beyond the limits of the array. So if you notice, the array has 5 elements. So the for loop should be go up to 6 because the condition hits before 7 actually. So what happened is, let's compile this code. We use the C++ 11 standard. We call the executable myArray, and when we run myArray, as he noticed probably, so basically covers all the values 0, 1, 2, 3, 4. Then there is a 0 and another number. So notice that it's going beyond the limits of the array. And initially you can get any kind of value, basically garbage. Sometimes, if you are lucky or not, what happens if when you are looping in this way and you are going beyond the limits, if it's accessing memory that doesn't belong to any other program, it will return some values randomly. It can be 0, it can be something else. If it is hitting memory that belongs to another program, it may crash with a segmentation fault error. Somehow that is a good sign because it's actually letting you know that there is a problem with the code. We're going to discuss this further when we do the debugging class. Okay, that's something that you need to be aware. There is no way, or there is no sign that the compiler will tell you, okay, you may be going out of bounds unless you put some flags in the compilation lines, and you may keep working with numbers that has no meaning whatsoever. Okay, any questions? Okay, this is another example. I think some of you were asking about this, maybe last class or when we discussed the assignment or in the email, I don't remember exactly. But the question is, or the point is, how we pass arrays to a function. Okay, so in this example, we had a function that is called SumArray, SumR, and it will receive an array of integers and the size of the array. Okay, and basically initialize a variable called total, which accumulates the values. It covers the size of the array, the elements. It adds the values to total and basically returns total. Very simple function. It basically adds all the elements in the array and returns the value. I'm using the constant type here for integer for the arrays, for the size of the array equal 8. My array is called cookies. It has the size of 8 and it has some values there. Okay. Next thing I do is just call the function, and the values return in this integer variable sum. Okay. I'm passing the array and the array size, right? And basically, I'm outputting the value that I get from the function. All right. So if we compile this code and we execute, basically we get the total number of cookies containing the array. So the addition of all the elements in the array. Okay, so this is an example of how to pass array. Something to notice is you always will have to pass the size of the array. Okay, so you pass the array and the size of the array. Okay, let's see another example of this. So same function, more or less. Now the difference is I add this line here. It's an arbitrary line I add, but just to make one point. Okay. So that line, what it's doing is adding to the first element of the array 10 arbitrarily. Okay, you will see why. Something I forgot to mention is, but we covered this, I think, is arrays in C++ start in 0. The indexing starts in 0. But I think we discussed that too. So it's the same piece of code. Now the only difference is that I have another variable where I'm calling the sum array function for a second time. So I call it first for having the total number of cookies in that array, and then a second time. Okay, and then I'm outputting both values that I get. Right? So we compile the code and we run it, and the total number in the first time and the second time is increased by 10. Why is that? Because that line I add here of adding 10 to the first element. The point being is that when you pass arrays, actually you are passing by reference. Remember this difference between passing by value and passing by reference? Very quickly, when you pass by value, the computer is making a copy of the variable. So whatever happens inside the function doesn't affect the variable in the main loop, in the main function. When you pass by reference, the computer is actually getting a pointer to the variable. So whatever I do with that variable inside the function, it will be reflected in the main function of the code. Okay, and this is what happened here. The bottom line is that when you pass arrays, actually the function is receiving a pointer to the array. There are different reasons why is this. Probably the most likely is to make it more efficient from the point of view of the computer and don't do a duplication of the whole structure. Okay, but that is for sure something that you have to be aware of. Right? That clear? Yeah, any questions? No? Good. So basically, this is the point I was making. In C++, the functions pass arguments by value, but not by reference, with the exception of the arrays. So an array, basically, you can see an array as a pointer to an allocation of memory. So therefore, when the function gets an array, what it gets at the end is that pointer to the allocation of the memory where the array lives. And a way to protect those arrays from being modified is to use the constant flag in the prototyping of the function. Remember when we talk about the prototype and the implementation of the function? So when you define the prototype, you put the const, and basically the compiler will know, I don't want to touch this array, and I will create a copy for you. Right? So basically, this is going to make the point more explicitly that we can deal with arrays as pointers. So when you think about arrays, just think about as a pointer to a linear structure in memory. We're going to discuss this a bit more concretely. But this is an example. So let's say that we define a couple of arrays there, but by using just what is called the dynamic allocation of arrays. So we had, actually this is a static one, so we had an array of type float with 3 entries, and then we had an array of type B. This is a dynamically allocated, where basically we define that B is a pointer, and it will have allocate memory for 3 floats. That is basically what they say in new float 3. Then we had another pointer, P, which actually points towards the array A. Okay, that's the third definition there. Star P equal A is a pointer that is actually pointing to the array A. So now we have a for loop where basically we have the pointer. So this basically is doing what is called some pointer arithmetics, and it's the way how to access the elements of P and assigning the elements of A. Okay, I had a pointer B, and I have an index I that will go from 0 to 3. And if I ask for the pointer of B plus I, basically what I'm doing is moving in the indexing of the array B. Okay, so it's the same as saying B of I. Is that clear? Then basically what we are doing is we are printing the pointer, and we are going to print the variable P, which is a pointer type, and we are going to print the pointer of P. What is P pointing to? Okay. We are going to increment 1, do the same, and so on. So any guesses of what we are going to get when we print P and star P? What do you think we are going to get there? So we compile this code, we run the code, and when I print P, basically what I get is this weird number. It's a hexadecimal number. It's a memory address. Okay, that is what a pointer is underneath. It's the location in memory, so the computer knows where to go and look for the data. When I print the star of P, you can think about the star of P as the interpretation of what is P pointing to. What is the content of the pointer of P? Okay, so P, a pointer, is the memory location. A star of P is what is in that location. Okay, so every time I print a start of P, I actually get the values that are contained in the array that was defined by A.
Star static
Is better than A, if you wish, because A is statically allocated, B is dynamically allocated. But yeah, it's basically an array. It's kind of the same structure. The layout in memory is exactly the same. The way to access it sounds more complicated, but it's more powerful at the end.
In this case, you need to have the same.
Yep.
So what's better in this?
The advantage will come later. So you can start to create these two-dimensional arrays or higher dimensional arrays, and then you can actually access them by doing this kind of arithmetic. And the bottom line is that when you use these libraries, like linear algebra libraries, when you do operations, if they are laid out in the memory in a particular way, they are way faster. We're going to see this today. Yep. No, so the rule is, and it's a good point because I don't think I had the delete statement here. You only delete the ones that you use new to create. Only P. Yeah, that's right. Okay, so for each new that you have, you need to have a delete at the end.
Avoid it. Don't any. No.
Yeah.
It's just to show and they code does it. I know what it does exactly. But
yeah. It has some advantage underneath, but it's more obscure. And I think if you look carefully, for instance, when you have let me see if I have an example here. Probably there is another one. But basically, it's what Rancy was mentioning. Either you can access the element by doing B of I or doing star B plus I. It actually will work even in multidimensional arrays. So having the two brackets, I think we have an example. Okay. Any other questions? So let's take a look at what is going on actually to try to understand a bit deeper how this thing with the pointers work. So one of the things that start to get interesting and we need to understand is how the memory works at the very low level. And at the very low level, the memory is just a linear structure. Okay, so there are no actually more than one-dimensional structures in the memory layout. So when we have a matrix or a two-dimensional array, how is actually this saved in memory? So let's say that we have that data array, which is a a two-dimensional array. It's a 4 by 4 elements, so it's a 4 by 4 matrix if you wish, and it has entries 1, 2, 3, 4, etc. So how that happens, how that is posted in memory? Well, what happened is, actually, I told you the array is nothing else than a pointer, which points to a linear structure initially of 4 elements, so that's the first 4, and then it will have 4 rows or columns, depending on the language, which contains the data. So the first one is a pointer to 4 slots, and then there are 4 more pointers that point to another 4 slots where the data is actually stored. Okay. So I mentioned that how the slots are organized by rows or columns depend on the language. And why is that? C++ is what is called is a row major language. For instance, Fortran is a column major language, but it means each of these pointers are pointers to rows. So when I had this two-dimensional structure before, each of those pointers are going to be pointers to rows. So if I want to create this 4 by 4 matrix, I will have pointers to the first row, second row, third row, and fourth row. Okay? So in this case, a 3 by 4 matrix, which can be stored as 1, 2, 3, 4, 9, 8, 7, 6, 2, 4, 6, 8. You can see that each of these elements that comes after are rows defined. If this was Fortran instead of C++, that will be rows. It will be a 4 by 3, if you wish. It will be, sorry, it will be columns. It will be 1, 2, 3, 4, 9, 8, 6, 7, 9, 8, 6, 6, 2, 4, 6, 8. Okay. This is another detail. So if you are passing two-dimensional arrays into functions, and this is something funny that happens with C++, we mentioned that we always had to pass the size of the array. So think of this as an array of arrays. So we had to pass the size of the array, which corresponds to the third index, but also we had to include how many elements are in the second part of the array. Okay, so if this was a 3, like in that case, size will be 3. If it was a 4, like in the previous case, it will be a 4, but also you need to hard code sort of this other number there. It's just basically telling how much chunk of memory the function is going to receive in each of these rows. Okay? Any questions? Yes, it has to be in the head of the function, which is not ideal. So that's why we're going to see this pointer thing, because one of the nice things the pointer can do for you is forget about this. Because basically now I'm pointing to the location in memory where I will have my structure laid out. Okay. So this is another example where we're going to use the pointers to pass these dynamic arrays instead of the arrays itself. So I put my prototypes of the functions there. In the next slides, I have the sum array and the allocate memory. The allocation comes for deleting this allocated, to delete these dynamically allocated arrays. And the main function looks like this. So I have the number of rows and the number of columns, 3 and 4. Then I'm creating this double pointer. This probably is the new stuff here. I have this double pointer, which means that if you think about this, is a pointer to a pointer of P, which basically has the memory of, or it will have the size in memory of integers given by the number of rows. Okay, so this comes to the idea of this. P is going to be this double star P, which points to these things, which are going to be pointers to structures of the other size. Okay, so then for initializing, we basically do a double for loop because it's a two-dimensional array, a matrix now, I index and j index. And notice that now we had to allocate also memory for each of the pointers within the first level of the two-dimensional array. So P of I will be a new of type int, but now the number of columns. Okay. Then when we are in the second layer of the for loop, we loop over the j index, and basically now we can start to assign the values. And notice what Rancis was mentioning. You don't need to use the double star P. You can just go by the bracket notation. So I can access as it were any kind of array like P of Ij equal and some given value, here I plus j. Okay. If I were using, maybe it's not a good idea to mention, but if I were using the pointer notation, I will have something like star star P of, I will have star star parenthesis P plus Ij, or something like that. Okay, but you don't need to worry about that. You just can use the bracket notation I of j. So the only complication is when you are actually allocating the memory for the arrays and how you do it. But you do in 2 steps. First step, you allocate the first pointer, the first level of pointers or layer of pointers, and in a second step, the allocation for the memory of the columns. Yep. It has to be I times the size of the element. Yeah. So I don't want to get into detail, but basically, yeah, you need to consider the step in memory that you are jumping. So it has to be multiplied by the size of the type, in this case, integer. Not necessarily, so we are going to look at that. Okay, so here we're initializing, we are printing what is ever initialized, a break line, and then we are basically printing the total of this, of adding all these numbers together in the matrix, deleting the allocating the memory and returning. Okay, and this is how the functions look like. So the sum is basically just a sum. What is different is that we are receiving a double pointer here. So, but by having the double pointer, I don't need to know the dimensions hard-coded in the brackets. So that's the advantage of using the pointer notation. We need to know, of course, the number of rows and number of columns, sure. So we can run our summation there. But basically, when we access the elements in the matrix, we just do P of Ij. So brackets notation. The allocating is very simple. You do as many the allocations as you have allocated. So there is a for loop because there was a for loop for accessing the new statements. And then there is a delete because of the first new statement that we had at the beginning with the double star P. Okay, so the golden rule is as many deletes as news you have in the code. Okay. Compilation is as usual, and so what it says is, okay, P, which is this matrix, has these values, and the total is 30, which is the addition of all these values. Okay, any questions? Good. Okay. Let's take a look at this. So these 2 functions are allocating memory for a matrix. Can you tell me which is the difference? What do you think is the difference between one allocation and the other? In the first one, so the first line is the same in both, right? So we have a float, so it's going to be a 2-dimensional array of floats, and it's basically allocating floats for n numbers. Okay. The difference comes how we allocate the first element in the second one, and the for loop. So in the first one, we are basically looping on I from 0 to n, and we are allocating columns, basically floats for m, in m, the other dimension of the array. In the second case, what we are doing is the first element of the pointer is going to have the whole chunk of the matrix, m times m allocated. See that? New float n times m. And then we are looping over I, starting on 1, and basically we are putting, instead of allocation, we are setting each of the elements to the address of A of 0 times A of 0 IM. Okay? And then we are returning the pointer, nothing different there. The main difference is how we are allocating these things. What is going on here is more clear maybe with this picture. The first method, what it's doing is what we did before. We allocate 4 elements for the first part of the array, and then we allocate pointers for the remaining rows or elements of the array. In this other case, what we are doing is we allocate again the first part, the first layer of the array, but then we allocate for each of these elements chunks of memory. Okay, that is done in the inner loop, in the inner part of the loop here, where it basically says reserve continuous chunk of memory or continuous pieces of memory for this array. The difference at the end is how it's going to be the layout in memory of this array. So this thing is better because when the computer has to go and read for the data, it can read continuously all the way through. When you had to do these kind of things, then that chunk of memory may be in one part, in a different part, the second one, and so on. So the computer will have to jump between different addresses in the memory, and then at some point it's a bit time consuming. On top of that, the libraries, the specialized libraries that do linear algebra, fast Fourier transform, solve linear systems, they are optimized for that kind of layout in memory. So that's why whenever you can, try to allocate memory in this way and not in this way. Yeah. No, because you are allocating the memory, right? And you keep the pointer. And unless someone else releases the memory, that memory remains there. It's a good question. We release the memory. I don't know. I didn't show that. But you basically release like this. Okay. You need to be careful though, because now the allocation is a bit different. So you can basically release in 2 steps. Can I have an example, please? So depending how you allocate, you delete differently, right? So in the first case, the example shows how to delete each of these levels, and then you delete the upper level, right? So you delete each of these rows if you wish, and then you delete the double pointer, which is data in this case, or P or A in the other case. In this case, you can delete all these chunking ones, and then the pointer. Sorry, say when we refer to. Yeah, I mean. Oh, you mean okay? I think I know what you mean. Here? No, here. No, I'm not sure I understand the question, but let me see if I can show you. So where that allocation is happening is here. So let's say I have, in this case, 4 times 3. So I will have 12 elements of type float. So the type float will basically tell me, I'm not sure I understand the question, but basically the type float is telling me how much memory I need for storing a float type in the memory, right? And then I need 12 of those. So basically when I do the allocation, I put like 12 of these guys all continuously.
If you size of
No.
So,
All right.
typically,
Oh, I see.
right away, biases is the delete has deallocate same amount of bytes. That's why it goes perfect. I better look up how much. Really remember that in the first case, 0, 1, 3 have 4 elements.
Yeah.
The subsystem that you don't have access to members, 0, 1, 1, and 4 0 and
12,
16.
16. Yeah, it's 16 in that case.
16. But it hasn't remembered anything but one. Right?
Yeah.
So you only should.
From 0?
No.
The graph is accurate. That pointer, coordinate one points that address. Right? But there's no memory allocation associated. One point that you row.
So basically, you cannot delete one element of the green array per se. It's the whole thing.
Allocation.
Yeah.
Those are in pairs. They do it one and allocate.
Different.
You'll always write.
Yeah, together. Yeah. Any other questions? It's a bit complicated at the beginning, but you will get used to it.
So, how rate of point stack.
Well, they can both.
Yeah.
Because one is dynamic number rows, the other is. So those are separate. He sees the matrix as.
Don't have to say say 4 squares. For that sense that I'm at least adding say.
Well, no, you don't have.
Yeah.
But it can be either or, so you can have a second part.
You can play with two parameters if you
The
wish.
best
Right?
thing is just do it. But language.
Okay. Any other question?
Where type. Don't call it have the same size.
That's right. But yeah, but that size of well, so you
I
can have
see.
a function of x equals size of x.
Size.
Oh no, that is possible. Don't know it. At some point, you probably know it.
You still have to have a parameter there, an m, right? But it doesn't have to be hard-coded like 5.
But it does mean that if you're in a file, you don't know, I first that file, find that out. But I tell you, I know
More questions?
Like language has to see.
if that was the case, we all would be like,
All right. So this one. Okay. So this is how they allocate. Someone was asking how we deallocate. So for the two different methods, how we deallocate. So that is as we did before. We deallocate element by element, and then we deallocate the point array. And in the second case, we deallocate. This is the first element of the point array, and then the point array. Okay. So as Rasi was mentioning, you had to pair the news and the deletes basically.
Allocation is safe because otherwise you would just overwrite or
It's good practice. Okay, so when your program ends, basically the operating system, the modern operating system, take care of any remainder that may have not been deallocated. But imagine that you had a program that is a very complex program and it calls a lot of functions, and there is a function that allocates a lot of memory and doesn't deallocate it. So you may run out of memory if you are not, if it's not done properly. The other thing is, this is when that happens, it's called memory leaking. So it's like memory is leaking because you don't deallocate. So we're going to check that or learn how to check that in the debugging lecture. But this is good practice on the one hand, but it can also lead to problems like running out of memory if you don't do it in your own program. Okay, so this is kind of related again to how we lay out those arrays. Which of these sums do you think is faster? And in this case, basically we are going, it's basically a loop in I and j, where we are looping by rows first and then by columns. Okay, the way I'm accessing the array is exactly the same. It's a double pointer p and then p of ij. And in this case, the only difference is I had switched the way in how I sum. Okay, so the loop in I think is explicitly shown, is inside instead of outside. So the outer loop is done on columns and the inner loop is done on rows. Which one do you think is faster and why? Any guesses? Oh, there are two. So they, yeah. Okay. So the idea is right. The faster is the one that will go just in one stride, but I think it's the second one because the way that is accessing. Yeah. So it's the way that is accessing the elements, because remember C++ is row major, so it's going to store by rows. So the one that goes and access row by element by row is going to hit a straight line the memory. Okay. And I think this is just an example. Basically, unless that you specify or you allocate the memory in that particular way that we did before, the blocks of memory don't need to be continuously allocated in the memory. So by doing that, you can basically read once and do the summation straight. Oh, it was the other way around? Sorry. Yeah, number of rows. Yes, you're right. Okay, was that clear? Sorry, I thought that my example was the other way around. But basically, yes, it's sum all across them. Okay. Same. So much we have. Okay. So there are so for dealing with multidimensional arrays or matrices in particular, there are several packages that you can use that are already designed. So one of the themes of this course is don't reinvent the wheel unless that we ask it for. Try to use as many packages are already in place so that you can take advantage of optimization that is been done, debugging that has been done on the code, those kind of things. So there are a couple of different packages that does already this. That there are packages that deal with matrix multiplication, inversions, decomposition and factorization, even eigenvalue calculations, things that appears in different things. Many of these has been also been parallelized so that you can take advantage of multi-core computations. The ones that we are going to see in the second part, maybe in a week or so, or maybe 2 weeks, are BLAST, which are basic linear algebra systems, and LAPACK, which is a linear algebra package, and there are parallelized versions of these ones as well. But today we are going to take a look at some examples. The first one is the one called Eigen, which is freely available there. And it's pretty easy to deal with, and it's very straightforward to do operations with matrices, and of course, do eigenvalue computations. So only thing you need to do is install the package, and then include the header for Eigen, in this particular case, the dense matrices. And basically, you define the matrix in a template way. I don't remember if we mentioned templates, but it's kind of wildcard for defining containers with different types. So in this case, from Eigen, I will use the matrix object or container of type float and 2 by 2, and I have 2 elements, A and B, that are going to be of this type. Okay, and then I can just use the double less than symbol for assigning values. So that is actually useful if you want to read from the command line or standard input. And then you can just basically print the matrix. Sorry, this should be a P, an A. Addition, subtraction, multiplication, the straight operations and it will basically look more or less as you will expect. Okay, so you compile, you run the code, you get your matrix P, A plus B, A minus B, a scalar times a matrix. You can either do vector matrix multiplication. So in this case, matrix of type flow 2, 1 is a vector. Same thing for U and B, which are initialized, by the way, in that way. And then you can do matrix multiplication, matrix vector multiplication. You can even compute the transpose of a vector and multiply by the matrix, or do inner scalar products of a vector with its transpose if you wish. Okay, so the typical kind of linear algebra operations for matrices are all there. It can even solve linear systems like AXB, AX, A being a matrix, X being a vector, equal B another vector, and solve for X. Whenever you do this computationally, there are different methods. One is called the LU decomposition. We're going to have a lecture or two reviewing linear algebra. So basically, the LU decomposition breaks the matrix into a lower triangular and upper triangular matrix. And what does is solve for B. Solve for X in B an independent vector. So you can either use again the matrix, the vector type, and finally get the eigenvalues and the solution for the linear system. So all this is included in Eigen. Right? Another example that we are very proud because Francis developed this is rarray. It deals with multidimensional arrays dynamically. So you can download rarray from GitHub. There are a bunch of different things or headers that you can include for doing I/O and computations. It's very straightforward to use. So use a similar syntax like rarray, double, and 3 is going to create a 3x3 matrix in that case, of size 3. In this case, someone was asking about initializations. The library brings its own method for initializing. So A fill 4 will fill the matrix with 4, so whatever value you give. Okay. You basically access the elements of the matrix in the usual way. In this case, it's a 3-dimensional matrix, so IJK will basically give you the index. And defining format, I think there is documentation that says why defining format in the outputting. So you can read about that. It's very likely that you will have an assignment based on rarray, so get familiar with it. What else? Oh, yes. There is a bunch. So one thing I forgot to mention, and we are kind of almost by the end, so this lecture didn't cover as expected all the material. So, but there is, so the data structure we're probably going to revisit next class. But at the end, there are some extra material. It's like an appendix of the slides. There is information about rarray in particular. Review that, and if you have questions, please let us know by next class. But something before finishing that we had to let you know, because whenever you are going to search for multidimensional arrays in C++, you probably are going to find this, which is the vector class. And the vector class sounds very, very interesting, but it has its complications, in particular when you want to deal with higher dimensions arrays. So the vector class is a class that comes automatically with C++. The problem is that when you do with these high dimensional arrays, it doesn't allocate things continuously. So at the end, it can be more a trouble than something that helps you. So this is an example how to do it, but we're not going to discuss it because you're not going to use it, right? And yeah, that's it for today, I think. Any questions? We're going to discuss data structure next time. We're going to discuss data structures and Gits. Yeah, sure. Oh, for the report, plain text or PDF is okay. We suppose it's just a description of what you did for modularizing, breaking into parts, and make it compile with your main file, and that's it. Right?